Hi everyone, Mr. Markwick. In today's video, we're going to be looking at a problem we can use linear programming to solve. In today's problem, you'll notice there's actually more than one optimal solution. We'll get to that in a minute. I will also save a little bit of time using technology to graph the feasible region or the simplex for this problem. But let's go ahead and look straight at the information we have and then look at solving the problem using those 6 steps again from the Hazy textbook. So a store can sell every gift basket it is able to make. So I guess that part's important because we're not assuming that they're selling all the baskets. They're saying that they can sell them all, so they will sell out regardless of the combination of large and small baskets. I'm jumping ahead a little bit here, but small baskets contain 5 chocolates, 1 balloon, and 12 roses, and large baskets contain 10 chocolates, 6 balloons, and 12 roses. The shop has access to 80 chocolates, 36 balloons, and 168 roses. Small baskets sell for $20 and large baskets sell for $40. What combination of baskets should the store make in order to maximize their profit? So the 2 products we have here are the small basket and the large basket, and the resources they're competing for are the things that go in those baskets: the chocolates, the balloons, and the roses. And you can see there is a limited amount of each of those 3 resources, meaning that we need to have less than or equal to each of those resources when we're looking at our constraints. Anyway, the first step is to explain or define in sentence form the 2 variables being considered. So for the sake of this, we are going to let X represent the number of small baskets which sell for $20, and we are going to let Y represent the number of large baskets. Now, the next step there is step 2, prepare a table to display the given information. Now again, your table can take multiple formats. I'm trying to work on the way I do it. So here I've got a column for the product, a column for the variable I'm allocating to each of those products. In this case, there are 3 resources that they're competing for. So I'll list those there, and that actually shouldn't be profit, it will be the income. So income here. We're not actually making $20 profit or $40 profit, but they're selling them for $20 and $40. So the first column there is the product. So the first product is the small basket, and the second product is the large basket. The number of each product, small, is represented by the variable X, and large is represented by the variable Y. Now, the first resource that they're competing for is chocolates. So in this column, I'm going to have chocolates. Now, in a small basket, there are 5 chocolates. Okay, so small basket, 5 chocolates. In a large basket, there are 10 chocolates, and there are 80 chocolates altogether that can be used to make up the combination of baskets. The second resource that they're competing for here is the balloons. So 1 balloon for small baskets. So what do we say? 6 balloons for a large basket and 36 balloons altogether. And the third resource that they're competing for is roses. So that can be in our final column, and there will be 12 roses in each the small and large baskets, and there is 168 roses in total. The income for selling, or the selling price for each basket, is $20 and $40 respectively. So in the table here, I'm just going to put 20, hopefully, and 40. Now, step 3 is to write the objective function in an algebraic form. So we're going to write an algebraic expression and state whether you are trying to maximize or minimize the objective function. In this case, we are trying to maximize the income for this store. So our objective function would be to maximize. And remember the objective function is based around maximizing that income, and therefore what we want to do is use the sale price for the small and large baskets to create an algebraic expression. So in terms of x, which is the small basket, 20x, which represents $20 per small basket, plus $40 per large basket, or $40 times by the number of large baskets we sell will give us the income. Okay. Next, it asks us for step 4 to state the constraints in algebraic form. Here, remember, we are writing the inequalities that reflect the limited resources that both of these products are competing for. So the next one is step 4, constraints. And I'll try and color code these so that the first constraint here will be in green, and it is representing the constraint for the chocolates. So 5x, so 5x plus 10y must be less than or equal to 80. Excuse me. So the number of chocolates in however many small baskets plus the number of chocolates in however many large baskets they make must not exceed 80, because they only have 80 chocolates. So balloons, we'll do the same with that based on the constraint there. So again, I'll change that to red. So this time it's 1x, or we could just write x plus 6y needs to be less than or equal to 36. The final constraint that we're looking at there is the roses, and this time it will be 12x plus 12y must be less than or equal to 168. Once you've got your constraints, you can draw your graph. I think one other thing that you do need to always consider, and most of these problems will have the additional constraints of x is greater than or equal to 0 and y is also greater than or equal to 0, because we can't usually make a negative amount of a product, or there's not a negative amount of time to do something. So generally the additional two constraints will always be x is greater than or equal to 0 and y is greater than or equal to 0. So in this case I have 5 constraints that I will graph to find my simplex or feasible region, because there are 3 resources giving me 3 constraints or inequalities, plus the additional 2 of x is greater than 0 and y is greater than or equal to 0, because in this case we cannot make a negative amount of baskets. Okay, so those 5 constraints, as I said, I'm using technology, so I'm going to pop those into a bit of a graphing package. I'm using the one from the Hazy textbook, and I've already put those values in. You can see here, if I just move myself over here, that the objective function, 20x plus 40y, $20 for the small baskets plus $40 for the large baskets, and we're trying to maximize the objective function. I have then put those 5 constraints as we've written them, as we just came up with them here. Okay, they're also written down here. And now all I'm going to do to look at the last part of this is to find the optimal solution, and when it occurs, give your answer in sentence form, is actually ask this program to solve it for me. Now, remember, you can obviously look at those vertices, okay, the coordinates of each of those vertices, and then substitute those x and y values into your objective function, okay? And the set of coordinates, in this case, the combination of x, small baskets, and y, large baskets, that gives us the greatest profit is the optimal solution, okay? However, if I did that, I would actually find that these two vertices here are my optimal solutions. So I'm actually just going to press here. This function actually allows us to solve it. It will do it for us. So I hit solve. You can actually see there are, in fact, 4 coordinates that are also parallel or overlay with that, I should say, rather than parallel, overlay with the objective function. So there are 4 solutions to this problem. And if I scroll down, it does the working out for me at coordinates 6, 5, so 6 small and 5 large baskets. At coordinates 8, 4, 8 small, 4 large, 10, 3, and 12, 2. The profit will be $320 at all 4 of those sets of coordinates, at all 4 of those combination of small and large baskets, okay? So my solution is, my optimal solution is any one of those combinations. So there you would write in sentence form that the store should make 6 small and 5 large baskets, or 8 small and 4 large baskets, or 10 small and 3 large baskets, or 12 small and 2 large baskets in order to maximize profit. Okay, so that's how you would finish it off. Now, one thing I do also want to point out, or maybe a couple of things, is that yes, I have said that previously our optimal solution occurs at the vertices or the corner points of this simplex or of this feasible region. These 2 points here are not on the vertices. Now, this is, I guess, where you may find an exception to the problem. If you have an optimal solution that, or more than one optimal solution, I should say, look at any coordinates along that line between those 2 optimal solutions, which will be vertices, and any, I guess, points in between those could also be possible solutions, will also be optimal solutions as well, okay? And keeping in mind that here, we are after integer solutions or integer pairs for our answer, because you can only make a whole basket, a whole small or a whole large basket. So here there are 4 coordinates of integer pairs that are the optimal solution, because yes, they appear at those 2 vertices or in between those 2 vertices, okay? Another way, so you may have, I guess what I'm saying is you may have 2 optimal solutions that appear on vertices, and if you do have that, then look to find, is there any other possible or feasible solution between those 2 vertices on that same edge of the simplex, okay? Because you might only have 2 optimal solutions and no possible solution or feasible solution in between them on the edge of that simplex, in which case there'll only be 2. Sometimes there's more, sometimes there's 3, 4, or even more. Okay, in this case, there are 4 possible optimal solutions for us, okay? And I know I'm talking a lot about possible and optimal solutions, but remember, here is a possible solution to the problem, making 1 small and 1 large, but that's not going to give us the optimal solution, which is the maximum profit. But all of these 4 coordinates will. Now, one other thing I will quickly point out before I wrap up this video is that you'll notice that linear, or these problems that we solve using linear program that have optimal solutions, more than one or multiple optimal solutions, if you look at the objective function, in this case 20x plus 40y, it will actually match up with one of your constraints or inequalities. In this case, it's matching up with this one here that I'm now highlighting orange on your screen, because the coefficient of x here, or the value of A, which is 5, is a factor of the coefficient of X up here, or A, which is 20. So 5 is a factor of 20. And also 10, or the value of B, coefficient of Y, is a factor of 40, or the value of B, the coefficient of Y here. Okay, so you'll notice that there are multiple optimal solutions when your objective function and one of your constraints in terms of the coefficient of X and both Y are either multiples or factors of each other. Okay, and that's one way of, I guess, identifying multiple optimal solutions before you even get to the graphing stage. Once you've written your objective function, once you've written your constraints in inequality form, you can then see that there are multiple solutions. Okay. Anyway, that's a lot of information to take in, but I guess, like I said, this is the exception to the rule. I know I've said those optimal solutions only occur at the vertices, but in this case, okay, if you have more than one optimal solution, check in between those optimal solutions on the edge of the simplex or feasible region to make sure there isn't any more as well. Okay, that's it, guys. Thanks for watching, and hope it helps.